High above the clouds, a silhouette moves with the silence of a ghost. This is not just an aircraft, it is a masterclass in modern engineering. Military drones, or unmanned aerial vehicles, represent the pinnacle of aerospace achievement. They are designed to operate in environments too dangerous for humans, staying aloft for over 40 hours at a time. But their greatest feat isn't just staying in the air, it is remaining invisible. To a radar dish, a drone with a 50-foot wingspan must appear no larger than a common sparrow. Achieving this requires a perfect marriage of radical aerodynamics and exotic materials, substances that defy the traditional laws of aviation. Today, we go behind the classified curtain to see how these silent hunters are forged. We will explore the chemistry of invisibility, the physics of subsonic flight, and the brutal manufacturing processes that turn raw carbon and chemicals into the world's most advanced aerial platforms. From the microscopic structure of radar-absorbent coatings to the massive pressure of composite-curing autoclaves, this is the story of how we build the impossible. Every millimeter of this machine is calculated for one purpose: to dominate the workspace of the sky without ever leaving a footprint. To understand the drone, we must first look at the very atoms it is built from. Aluminum is the king of commercial flight, but for a high-performance military drone, it is far too heavy and reflective. Instead, the foundation of a stealth drone begins with carbon fiber, specifically high-modulus pre-impregnated epoxy resins. These fibers are thinner than a human hair, yet when woven together, they possess a strength-to-weight ratio that eclipses steel. The process begins in a climate-controlled clean room. Industrial robots, guided by laser pathing software, lay down layers of carbon tape with micron-level precision. This isn't a random weave. The orientation of every single fiber is calculated to handle specific aerodynamic loads. Some layers are laid at 45 degrees to handle twisting forces, while others are longitudinal to provide rigid strength. This layup process creates a monolithic structure, a single, seamless piece of material that eliminates the need for thousands of heavy rivets. Rivets are the enemy of stealth. They create tiny edges that reflect radar waves back to the source. By using composite molding, engineers can create a perfectly smooth, continuous skin. Once the layers are placed, the entire wing or fuselage section is vacuum sealed in a plastic bag to remove every bubble of air. Even a microscopic pocket of oxygen could cause a structural failure under the high G-forces of combat maneuvers. This skeletal frame is the first step toward invisibility. The raw composite layup is soft, much like a piece of heavy fabric. To transform it into a rigid, flight-ready component, it must undergo a baptism of fire and pressure. The drone parts are rolled into a massive machine called an autoclave, essentially a giant high-tech pressure cooker. Inside, the environment is strictly controlled. Temperatures soar to over 350 degrees Fahrenheit, while the internal pressure is ramped up to over 100 pounds per square inch. Under these conditions, the resin infused in the carbon fibers begins to flow, chemically bonding the layers into a single, indestructible molecular matrix. This process, known as cross-linking, creates a polymer structure that is incredibly stiff and resistant to heat. The autoclave cycle can last for over 12 hours. During this time, sensors monitor the part for any sign of thermal instability. If the temperature rises too fast, the resin could cook, becoming brittle. Once the cycle is complete, the parts are slowly cooled to prevent internal stresses from warping the shape. What emerges is a component that is lighter than any metal, but capable of withstanding the immense pressures of high-altitude flight. This is the bone of the drone. Now it needs its skin of invisibility. A drone's shape is its first line of defense, but its second is much more mysterious. This is RAM, radar-absorbent material. Standard aircraft reflect radar energy like a mirror reflects a flashlight. A stealth drone, however, is designed to swallow that energy. The secret lies in a specialized coating, often referred to as iron ball paint. This isn't just aesthetics, it is a complex chemical soup filled with carbonyl iron particles or ferrite. These microscopic spheres are coated in an insulating polymer. When a radar wave hits the surface of the drone, it doesn't bounce back. Instead, the magnetic properties of the iron particles convert the electromagnetic energy into heat. That heat is then dissipated across the surface of the aircraft. Essentially, the drone is turning the enemy's radar signal into a tiny, harmless temperature increase. Applying this material is an exact science. The coating must be applied at a very specific thickness, exactly 1/4 of the wavelength of the radar it is designed to defeat. If the coating is too thick or too thin, it becomes reflective again. Technicians use handheld ultrasonic gauges to check the depth of the RAM across every square inch of the drone's body. It is a tedious, high-stakes process where a deviation of a few millimeters could mean the difference between a successful mission and a detected one. In the world of stealth, right angles are the enemy. A traditional tail fin, the vertical stabilizer, is a massive radar reflector, acting like a billboard for enemy sensors. To solve this, many advanced drones use a flying wing design. This eliminates the tail entirely, creating a smooth, blended profile that scatters radar waves in directions away from the receiver. But removing the tail creates a massive engineering problem: instability. Without a tail, an aircraft naturally wants to tumble through the sky. To keep the drone stable, engineers utilize split ailerons and complex fly-by-wire computers. These computers make hundreds of tiny adjustments per second to the flight surfaces, keeping the aircraft level. This is relaxed stability flight. The drone's very shape is designed to be invisible to S-band and X-band radars, which are the most common frequencies used by surface-to-air missile systems. The leading edges of the wings are swept at precise angles to ensure that any radar energy that isn't absorbed by the ram is deflected away at an angle. The result is a planform alignment, where all the edges of the aircraft are parallel to only 2 or 3 directions, concentrating the radar reflection into very narrow spikes that are easily mistaken for background noise by an operator. Radar isn't the only way to find a drone. Heat-seeking missiles look for the glowing infrared signature of a jet engine. To counter this, engineers use serpentine or S-duct intakes and exhausts. In a standard jet, you can look straight down the tailpipe and see the white-hot turbine blades. In a stealth drone, the engine is buried deep within the fuselage. The exhaust travels through a curved duct lined with heat-shielding ceramic tiles. This S-shape ensures there is no direct line of sight to the engine core. Furthermore, the hot exhaust gases are mixed with cool ambient air before being ejected through a flat, slit-like nozzle. By flattening the exhaust plume, the drone increases the surface area of the hot gas, allowing it to cool much faster in the atmosphere. Some advanced drones even use the skin of the aircraft as a heat sink, circulating fuel through the wings to soak up engine heat before it can be detected. This thermal management system turns a screaming jet engine into a whisper of warm air, making the drone nearly invisible to infrared sensors from the ground. It is a masterpiece of thermodynamic engineering, hidden away where no one will ever see it. With the body and skin complete, the drone requires its internal nervous system. The avionics bay is the brain of the aircraft, housing the flight control computers, the GPS navigation modules, and the satellite communication arrays. Because there is no pilot on board, the drone must be capable of a high degree of autonomy. If the link to the ground station is severed, the drone's lost link logic takes over, allowing it to navigate back to base or orbit a specific point using its onboard inertial navigation system. The communication antennas are buried under radomes, specialized composite panels that are transparent to the drone's own radio frequencies but opaque to enemy radar. This allows the drone to transmit high-definition video and sensor data to commanders thousands of miles away via satellite. Every wire in the drone is shielded against electromagnetic interference, ensuring that the heavy electronic noise of a modern battlefield doesn't scramble the drone's delicate sensors. These systems are tested in anechoic chambers, rooms lined with foam spikes that absorb all radio waves, simulating the vacuum of open sky. Here, engineers ensure the drone doesn't leak any electronic signals that could give away its position. It must be electronically silent as well as physically invisible. Before a drone can join the fleet, it must prove it can survive the brutality of the real world. In the structural test lab, the airframe is subjected to torture tests that simulate years of flight in just a few weeks. Massive hydraulic rams pull and push on the wings, bending them until they look like they will snap. This is to ensure the carbon fiber matrix can handle the G-loads of high-speed turns and the violent turbulence of high-altitude jet streams. Next, the drone enters the environmental chamber. Here, it is blasted with freezing temperatures of -60 degrees Fahrenheit, followed by the blistering heat of a desert runway at 130 degrees. Extreme humidity and salt spray are introduced to check for any signs of corrosion or delamination in the composite skin. Finally, the drone is placed on a pole in a radar cross-section range. Engineers beam radar waves at it from every conceivable angle to ensure the ram coating and the stealth geometry are working perfectly. If even a tiny hotspot appears on the radar screen, the drone is sent back for coating repairs. Only when its radar signature is confirmed to be smaller than a golf ball is the drone cleared for its maiden flight. This is the ultimate validation of thousands of hours of engineering, the birth of a silent guardian. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click 1 to keep watching. I will see you in the next one. Thanks for watching.